Hi class, we are now on 7.9. We are almost done. We have one more section after this. This is determining enthalpies of reactions from standard enthalpies of formation. Something again you should have covered in Chem 111. Hopefully this starts coming back to you as we work through it. So the standard state is the state of a material at a defined set of conditions. If it's a pure gas, at exactly 1 atm pressure. A pure solid or liquid in its most stable form at exactly 1 atm pressure and temperature of interest, which is usually 25 degrees Celsius. And substance in a solution with a concentration of 1 molar. So the standard enthalpy change, you see, has this little dot here, a little circle, is the enthalpy change when all reactants and products are in their standard states. That's what that means. The standard enthalpy of formation is the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. So the elements that make up that compound. The elements must be in their standard states. And we'll cover that right now. Standard enthalpies of formation, this is just another page of review. The standard state of a substance is the state in which the substance is most stable at 25 degrees Celsius, 298 Kelvin, 1 atm pressure. The standard enthalpy of formation has an F, is the enthalpy of formation of 1 mole of a compound from its constituent elements in their standard states. So these are in their standard states. This is what we want to make, so these would be the constituent elements. Note that the delta HF, we'll just call it that, of any element is in its standard state is 0. So if we take a look here, here are some standard enthalpies of formation for some compounds, and the state it is in does matter. You can't just pick water for liquid when you mean water for gas. There are two different values for this. So it's very important that you make sure that not only do you look up the correct compound, but you look up the state that you need and not just a generic one. If there's more than one state, it will also be listed. Okay, so using this to calculate the standard state of formation to calculate the standard enthalpy of the reaction. So what we do is we look up the formation values and we plug them in with products minus reactants from a balanced equation, and that will give us our value of an enthalpy of reactions when the standard state. When the reaction involves multiple moles of a product, then you have to also multiply that. So that would be on the outside, M representing the moles of the products and representing the moles of each reactant. And if you had several products, then you would group this together and you would group this together. Okay, so calculate the standard state, the standard enthalpy of reaction for the complete combustion, I know I'm probably not saying that right, sorry, combustion of 1 mole of propane at 25 degrees Celsius and 1 atm. So let's take a look at what we have. We have 2 reactants and 2 products. So first we need to calculate the sum of the standard state of formation of the products. So we had a table that's listed here, and the information is here. So one of the things we could look at is for the gas. So if we see it is here, propane, it's a gas, so we have it there. If I pick the right one, I did not. What did I pick? Propane is a gas, 393. Hold on. 390. Sorry, CO2, carbon dioxide is the product. Yeah, I'm not looking at this thing right. CO2. Yes. Sorry about that. See, I'm just testing you guys to make sure that you're paying attention. This is the products first. So yes, the CO2 is there as a gas, and we pulled the value out. That means always for 1 mole of that compound. And we have 3 moles of it in the reaction. Then we have 4 moles of water, and we would get that information for the water, which is the liquid, and then we would add these together once you multiply whatever those products are with their coefficients. So we end up with this value. Next, you do the same for the sum of the reactants. There it is, the 103. I know I wasn't going crazy. And there's 1 mole here, there's 5 moles. Now this is what I need to point out. When they say standard state, if it's in its natural element, in natural state, it's 0. So this tends to be for gases. Gases, this is a gas, hydrogen gas, H2, the diatomics, for instance, they're all 0 if they are in their diatomic form of a gas. So doesn't matter how many coefficients it has, if it's in a standard, in its state, that's standard state, it's 0. So the only one that's going to be accounted for here is the propane. Now we set them up and then we subtract. which makes this a positive, and that's going to give us our number, our value right there. So Hess's law. In 7.8, we calculate the enthalpy of vaporization of ethanol using Hess's law and the enthalpy change. Remember, we went from a liquid to a gas on that one reaction, and the enthalpy changes of two chemical reactions. So now you should be able to recognize that those two reactions show the formation of ethanol from its component elements in their standard states. So we're going to use standard enthalpy formations as an application of Hess's law. So it's just saying that we're going to expand more. And here's some information you can see. So we had the gaseous ethanol and the liquid ethanol. Remember, we used different products here, different compounds, and we adjusted and moved it around in order so that we could come up with just the ethanol. That was all that we were interested in. And here's an energy diagram for that. Here are more standard enthalpies of formation. I want to point some out. Bromine is a liquid, but it's a diatomic, so it is 0. Calcium as a solid is 0. Elements, so calcium element as solid is 0. Carbon as graphite, that is its natural state, is 0. But diamond is not its natural state, so there's a value to it. There's more of a list here. So H2O gas 0, oxygen gas 0. So you can see these are hydrogen, nitrogen, chlorine gas 0. So again, in its natural state, it will be 0. Here's silver as a solid, it's 0. We got sulfur as a rhombus. There's sulfur comes in different, well, I'm not going to get into that right now. That's 0. I really don't want to. And then sodium as its solid is 0. And I think that's it. So reactions of elements in their standard state to form 1 mole of a compound. If you're not sure of what these are, if you have the ebook, you should be able to get to the end and look at the appendix. And you should be able to understand what it's looking like. It should look like this. The delta HF with the 0 kilojoules per mole. And it'll give you what it is. And it should always give you the state of what that value means. Okay? So let's do one more so you can understand. Here we're given a reaction. This is what we want to produce. And we're given 3 different equations to get to this one. So there's 3 here, and basically I'm going to cut kind of through with shortcuts, and it's being adjusted in ways that it needs to be. So there's a positive here where it was negative, and things are being cut out. So if it ended up on one side and the other side, then we can cut them out, because what we want, our only interest is in this final reaction that's down here, and we end up with the value that we needed. How did we do that? Well, we took all the coefficients and we looked up. You have to look up every compound with its value, and then you add the products together, you add the reactants together, and then you get the final value. This is different from when we did it this way. So this is how we learned how to do it one way, but you can also learn how to do it this way, where you look up the values, then you multiply by the coefficients, and then that will give you the information that you need in order to produce this the bottom reaction.